Welcome to ATMOS 5000 Day 28. We're going to be focusing in on Chapter 2 of the Stull textbook, Section 2.3. This section includes all of the blackbody radiation laws, the Planck's law, the Wien's law, the Stephan-Boltzmann Law, and the Kirchhoffs Law, as well as defines the terms that we use in radiation and also the inverse square law. So it is an incredible amount of information that's contained in this one section. So for definitions, in this class we're going to be using flux, radiance, and irradiance as the three primary terms to describe the radiation in the Earth's atmosphere. So we have flux, which is the total amount of energy that's emitted by an object. It has units of joules per second, and a joules per second, recall, is defined as a watt, W-A-T-T. The radiance, which we'll be using I in this class, is the amount of energy coming from a specified direction, and we identify that direction as a solid angle, and therefore the units of radiance are going to be joules per second per steradian. Steradian is the unit of solid angle, and the units on irradiance are watts per steradian. And then we'll primarily be using irradiance in this course, which we'll be using the letter E to describe it. And the irradiance is the amount of energy that's incident on a surface in units of joules per second per meter squared. So that's equivalent to watts per meter squared. And I just want to highlight the fact that the variables that I've identified here as F, I, and E, the flux, radiance, and the irradiance, are not uniformly adopted and are textbook specific. So you just have to bear with the individual textbook that you use or some of the videos which I'll be posting, and realize that when we're talking about irradiance in this class, that'll be E, but if you use the Wallace and Hobbs textbook, the irradiance will actually be labeled as F, and so forth. So here we have the sun. The sun has an output of energy, and we can actually calculate the output of the energy of the sun, and we'll be doing that shortly in one of the in-class exercises. But we'll find that the flux from the sun is equal to 3.87 times 10 to the 26th watts. So that's basically 10 to the 26 joules per second of energy coming from the sun. Now, where does that energy go? It spreads out equally in all directions. So it spreads out basically in the shape of a sphere as it moves away from the sun at the speed of light. For the radiance, we have to use the solid angle. And just as a reminder, an angle in this case, theta, is just the arc length divided by the radius, the radial arm. And it's that angle that's subtended by that arc length. And of course, there are 2 pi radians in the circumference of a circle that way. Now, the solid angle is a little bit different. It's the ratio of the area on the sphere to the radius squared. So the area of that is defined as A in this case, divided by r squared. And if you wanted to integrate that entire area, so of course the surface area of a sphere is 4 pi r squared. So if you put in that for the A, then you would have 4 pi r squared divided by r squared, and that basically defines the fact that we have 4 pi steradians in a sphere. There we therefore have 2 pi steradians in a hemisphere. And if you are looking at the area subtended by, say, the moon, then that would be a much smaller area than 2 pi radians because the moon doesn't cover up the entire sky. And then lastly, we have the irradiance in watts per meter squared, which really, if we have the slab of atmosphere that's, say, 1 meter by 1 meter, and we have radiation that's passing through that slab, or is at least incident on that slab, the irradiance doesn't care what direction the radiation is coming from. All that it matters is that it's passing through that surface, or passing through, or is incident upon that surface. And so it really is direction independent as long as you're dealing with it from one hemisphere. And so that irradiance sums up all of the radiant energy coming from all of those different directions over the entire hemisphere. We next have to define black bodies and gray bodies. So a black body is a theoretical object which is a perfect absorber and a perfect emitter at all wavelengths. Now there is no such object known to exist in the universe, and so but it's a nice approximation for the perfect absorber and perfect emitter, and we'll be using that theoretical construct quite a bit in this course. But in the real world we have to deal with what we call gray bodies, which is everything else. And a gray body is defined as an object which is not a perfect absorber and a perfect emitter at all wavelengths. In this lecture, we're going to talk about the blackbody radiation spectral distribution. So Boltzmann was the first person to try and describe the spectral distribution of radiation from a blackbody. And what do I mean by a blackbody? A blackbody is a theoretical object that is a perfect absorber and a perfect emitter at all wavelengths. There is no such object as a blackbody in the universe that we know of, and so we refer to most things as gray bodies, which means that they're not perfect absorbers or perfect emitters at all wavelengths. They may be perfect at individual wavelengths, but not at all wavelengths. But the formulation that we're talking about here is for a theoretical blackbody object. And Boltzmann came up with a distribution for the blackbody radiation as 8 pi times a constant, which he named as the Boltzmann's constant, times temperature over wavelength to the 4th. And over here, this black line is essentially the formulation of Boltzmann for the blackbody radiation distribution curve, the spectral distribution. It has one problem though. The problem is that at short wavelengths, the limit of this distribution function, as the wavelength goes to 0, goes to infinity. So that would indicate that there's an infinite amount of energy at those low wavelengths, and we refer to that as the ultraviolet catastrophe. And it's clearly not what was actually observed when measurements started to be taken of blackbody radiation distribution. The blue line is the actual observed spectra for a blackbody object. And so we have a very strong disconnect between the Boltzmann distribution and the observed data at short wavelengths. So what happened is that Planck came up with a solution to this by fitting an empirical function to the data. And this empirical function is that the blackbody radiation distribution is equal to 8 pi hc, where h is now the Planck's constant, c is the speed of light, divided by wavelength to the 5th times the exponential of this quantity hc over lambda kt minus 1. And that formulation actually does a very good job of reproducing the data for blackbody radiation spectra. And that's the formulation for the blackbody radiation spectra that we will be using when we try and integrate underneath this curve to figure out the total amount of energy that is being emitted by an object, or we take a derivative of this function in order to find the wavelength of maximum emission. And those will be the next two steps that we do. So in the video you saw the description of Planck's law, and so I'd like to present this in the way that it's done in the Stull textbook, where we have E lambda star. So E lambda star is the irradiance in watts per meter squared at a given wavelength, and the star denotes that we're dealing with blackbody radiation. So this is the blackbody irradiance as a function of wavelength is equal to a constant C1 divided by lambda to the 5th, where lambda, of course, is the wavelength. And then we have this quantity E, which is the exponent, to the C2, which is a constant, divided by the wavelength times temperature minus 1. And so this essentially defines the blackbody radiation emission curve in terms of watts per meter squared. So the blackbody radiation curve that you see down below is obviously a function of both wavelength and temperature. So if we look at the top curve, which is the temperature equal to 6,000 Kelvin, you'll see that the area underneath that curve is larger than the area underneath the curve for the 5,000 K object. which means that the warmer the object, the more radiation is being emitted by that object. But you might also notice that the peak in the Planck radiation distribution changes with temperature. So as the temperature gets hotter, the wavelength of that maximum emission gets shorter in terms of wavelength. And Wien's law basically is a way to quantify what the wavelength of maximum emission is for a black body at a given temperature. And what it really is done mathematically is to take the derivative of the Planck radiation distribution function and set it equal to 0 to find the peak in the curve and then solve for the maximum wavelength. And Wien's law is really simple. It basically just says that the wavelength of maximum emission is equal to a constant divided by temperature. And if we use the constant 2,897 micrometers Kelvin, if we divide by Kelvin, then we'll get the wavelength maximum in units of micrometers. So what controls the type of radiation that's emitted by an object? Well, Wien's law basically tells us that the wavelength is dependent upon the temperature. And so hotter objects are emitting shorter wavelengths of radiation, and cooler objects are emitting longer wavelengths of radiation. So let's take a look at some different stars that exist in our Milky Way galaxy. So we have Arcturus on the left, which is a gigantic orange/red star, and it's much, much more massive than our sun, but it has a surface temperature of only 4,375 Kelvin, which is quite a bit cooler than our sun. Our sun in the middle is shown during a solar eclipse, where you can see the corona of the sun is basically white, and our temperature is about 5,800 Kelvin. And then we have blue stars. Rigel is an example of that. And the blue star has a temperature of about 11,000 Kelvin. So we can tell what the temperatures are by essentially using the wavelength of maximum emission. For Arcturus, we'd use orange-red. For the sun, we'd use green because green is in the middle of the spectrum. And if you add up all of the wavelengths together, then you'll end up with white light. And then if you use blue, you can, in Wien's law, you can actually figure out the temperature of these individual stars. And so there's quite a bit of variation in the temperature of the stars, and consequently, there's variation in the color of the stars as well. You can use this to your advantage when you are cooking your marshmallows on a campfire. So these same color schemes apply. So for example, the red and orange part of the campfire is the coolest part of the campfire. The yellow is in the middle temperature range, and the blue portions of the flame are where it's hottest. So if you're one of those people who like to set your marshmallow on fire, you just have to quickly put your marshmallow into one of the areas of the yellow or the blue, and it'll catch on fire pretty quickly. If you're like myself and you like your marshmallow slightly toasted, I'm going to keep my marshmallow up near the red and orange part of the flame so that it cooks but doesn't catch on fire. So next we have the Stephan-Boltzmann Law. And the Stephan-Boltzmann Law basically integrates the area underneath the curve of the Planck distribution. So where Wien's law took the derivative and found the maximum, found the peak in the distribution, the Stephan-Boltzmann law is basically just integrating the area. So for black bodies, we have E star, and once again the star is denoting the black body. So we have the black body irradiance is equal to a constant, which we're going to define as the Stephan-Boltzmann constant, which is 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth, times temperature to the fourth power. So you can see that the total amount of energy emitted by an object is a very strong function of temperature. And for gray bodies, the amount of energy that's emitted by that object, the irradiance, notice it doesn't have a star because this is a gray body, is equal to E, where E is the emissivity, which is a constant value somewhere between 0 and 1, and multiplied by the Stephan-Boltzmann constant times temperature to the fourth. And the emissivity is basically object dependent. Every object has a different emissivity. Now that we have a good handle on how much radiation we receive at the top of the atmosphere, we're going to start to look at what happens when that radiation enters into the Earth's atmosphere. So we're going to look at the disposition of monochromatic radiation. By monochromatic, we're talking about a single wavelength. And then you can expand that to multiple wavelengths. So we have an incoming irradiance from the top of the atmosphere. That could be S if you want to think of it that way. And we have an atmosphere, which I'm essentially saying is a one-layer atmosphere. It has an absorption component. Some of that incoming radiation is going to be absorbed. Some of it's going to be transmitted down to the surface, and some of it's going to be reflected off of that surface. Where we have our definitions of A is equal to our absorptivity, and A, by definition, has to be between 0 and 1. R is the reflectivity, which must be between 0 and 1. And tau is the transmissivity, which also must be between 0 and 1. So conservation of energy dictates that the total amount of radiation that we have, that radiation that's coming into the Earth's atmosphere can either be absorbed, reflected, or transmitted. But you can't create energy in this system. You only have a certain amount coming in, and you have to do bookkeeping to keep track of where that radiation is going once it enters into the Earth's atmosphere. If you divide both sides by the F of lambda, you'll end up with the following relationship of 1 is equal to the absorptivity at a given wavelength plus the reflectivity at a given wavelength plus the transmissivity at a given wavelength. And this is for a transparent surface. If that surface is opaque and the transmissivity goes to 0, then the only thing that can happen to that incoming radiation is either it can be absorbed or it can be reflected. So clearly the Earth's surface is an opaque object that can either be absorbed or that can either absorb the radiation or reflect it. The Earth's atmosphere is a transparent object that lets some of the radiation through. So we have absorptivity, reflectivity, transmissivity. We've already talked about emissivity, which was the fraction of the radiation that is emitted for an object relative to the blackbody. And I'm not going to go through the derivation. If you want to, it's in the Wallace and Hobbes textbook. But Kirchhoffs Law basically states that the absorptivity of an object at a given wavelength is equal to the emissivity of an object at that same wavelength. And it kind of makes sense. If you have an object that absorbs radiation at a particular wavelength, that means that that wavelength is able to excite some kind of vibrational mode in that object. And if there's a resonance with that particular frequency for the absorption, then that object will still vibrate at that same frequency and will be able to emit that radiation with an equal efficiency. So that's Kirchhoffs Law, and so I just wanted to include the emissivity here so that we could show the relationship between the absorptivity and the emissivity. So radiation that is incident upon the atmosphere can either be reflected, absorbed, or transmitted. The reflectivity is defined as the irradiance reflected over the incident irradiance, and it's also a function of wavelength. The absorptivity is the irradiance absorbed over the irradiance incident, and the transmissivity is the amount of the irradiance that is transmitted divided by the incident irradiance. And conservation of energy basically dictates that the radiation has to either be absorbed, reflected, or transmitted. It can't do anything else. So you end up with the since the absorptivity and the reflectivity and the transmissivity are basically numbers between 0 and 1, they're a fraction, then the sum of all of those fractions has to equal 1. And then we have Kirchhoffs Law, which is perhaps the easiest of all of the radiation, blackbody radiation laws, and it simply says that the absorptivity of an object at a given wavelength must equal the emissivity of that object at the same wavelength. And this has to do with the molecular vibrations that are capable of absorbing radiation. If they're capable of absorbing radiation of a given wavelength, they're also going to be capable of emitting radiation at that same wavelength. And next we have the inverse square law. So recall that the radiation that is moving from the sun is spreading out in the shape of a sphere. So what's going to happen is the surface area of that sphere is equal to 4 pi r squared, where r is the radius. So as the radius gets bigger, the amount of radiation, irradiance in watts per meter squared, is going to go down with the square of the radius. So we have essentially the irradiance at some distance 2 is equal to the irradiance, the blackbody irradiance at position 1, divided by the relative radii of the two objects. So you have the emitter, which is R1, and the distance from that emitter, which is R2. And of course, we can use that inverse square law to try and determine how the amount of radiation, how the solar constant basically changes with the radius that we have from the sun. Or in this case, what we're looking at is the solar constant S naught, which is 1361 watts per meter squared. If we want the solar constant at a given day of the year, then we basically have to compare our radius r with the average radius from the Earth and the Sun. So if our radius is a little bit further away than average, then our solar constant will be lower than 1361. And if we happen to be a little bit closer to the Sun than the average distance, then our solar constant S will be greater than 1361 watts per meter squared. Next, we'll define the albedo. The albedo is simply defined as the irradiance reflected divided by the irradiance that is incoming. So it looks at the reflectivity of an object. And if we look at the reflectivity of the Earth as a whole, the Earth reflects about 30% of the incoming solar radiation. So that means that the albedo is 0.3. However, it's important to note that the albedo varies significantly both spatially and temporally, and a lot of that has to do with the presence or absence or thickness of clouds, but it also depends upon the underlying surface. For example, ocean versus land has a very different reflective qualities, as does land versus ice or ocean versus ice.